presentation in the seminar series entitled Cutting Edge Advances Towards Personalized Mental Health. And the seminar series is hosted by my center, the Stanford Center for Precision Mental Health and Wellness. And today I'm delighted to introduce Adam Pines. Adam is a PhD candidate and an F31 fellow, and he is in the neuroscience graduate group at the University of Pennsylvania, and his primary mentor there is Ted Satterthwaite. Adam completed his undergraduate training in psychology at Loyola Marymount University, and that was focused in psychology. He then went on to complete his post-undergrad research training in my lab and was the lead coordinator on a very novel trial in which we were incorporating repeat imaging to understand who responds to behavioral intervention and why for depression. Adam's graduate work is centered on using recent advances in magnetic resonance imaging sequences and precision functional mapping to establish multi-level characterizations of individual differences in neurocognitive development. He will be defending his PhD soon, and we're thrilled that he will rejoin our center as a postdoc fellow in the summer. Adam's talk today is titled Multimodal Approaches to Delineating Neurocognitive Development, and he will discuss how he leveraged advances with imaging and data science to reveal both the nuanced detail and broadly generalizable principles of hierarchical brain reorganization and development. And join me in welcoming Adam. He will present for approximately 45 minutes, and we'll give you a heads up when it gets close to that time, Adam. And we will encourage everyone's questions and make this interactive. So if you have questions as we go, please put them in the chat. Adam, would you be okay if people want to jump in as you go, or would you prefer?
No, that'd be great if people are
okay, we can't hear you, so let's do a sound check.
I'm sorry, can you hear me now?
We can hear you. I think Leanne can't hear you,
okay.
So I'll let her know. Oh.
Okay, great. So all good. So over to you, Adam. Welcome.
Excellent. Thank you very much. Let me just share my screen here. I really appreciate that introduction, and overall it just means a lot to me for me to be here presenting to all of you. So thanks for the opportunity to do so. Feel free to interrupt me throughout or hold your questions, whatever works better for everyone here. But broadly, just thanks again for allowing me to give this talk. I'm going to be discussing my graduate work in this presentation, Multimodal Approaches to Delineating Neurocognitive Development. And again, although I'm happy to be doing this, I feel like we only get out of this what you guys take away from me giving the presentation. So feel free to interrupt me if clarification is needed. That being said, I want to start with just a basic consideration of the human lifespan. So typically, depending on our age, we're put in one of these different bins, be it 65 plus or as an adolescent or toddler. And from there, we extrapolate with varying degrees of accuracy certain properties about the person. And I'm going to make the argument that as either a clinical neuropsychologist or neuropsychiatrist, whatever label we want to give ourselves, the constructs of interest that matter to us about mental health, psychology, psychiatry are largely wrapped up in this broader lifespan developmental arc. And I'm going to give two examples here a little more explicitly. This first one is one of the more straightforward plots I made in my graduate work here, just showing an executive function factor score from a cognitive battery on the y-axis, and age on the x-axis. And when you know it, 23-year-olds tend to do better on cognitive batteries than 8-year-olds. Not terribly surprising, but this makes the point that when we're concerned about something like executive function in an individual or trying to evaluate where on the normative spectrum they are, their age is critical context for something like this. In addition to being critical context for evaluating individuals, different ages actually give us opportunities to study our psychological or psychiatric constructs of interest. This is just a schematic pulled from a nice paper showing the normative age of onset of a few different psychiatric disorders. And there are going to be individual cases that don't fit nicely into these bell curves, But largely, there are certain age ranges by which we expect psychopathology to emerge. And one step further from that would be to extrapolate that there might be something about the brain of a 6, 7, 8, 9, 10, 11-year-old that lends itself to the emergence of ADHD or conduct disorder in this time range. We might expect that this would be more normal to see the emergence of this condition in a 6-year-old, 7 or 8-year-old than schizophrenia or substance abuse. So by studying these age ranges explicitly, and particularly when using longitudinal data, studying lifespan maturation actually affords us the opportunity to glean additional insight into these conditions as well. So just to get a little bit more specific about the work that I'm going to be talking about today, I'm going to be talking about these developmental changes in the cellular microenvironment as assessed with diffusion-weighted imaging in functional networks. And this is really where the neurocognitive piece comes in as well. And then just super briefly on the last project I'm doing here, which is on global infraslow cortical oscillations, also measured with fMRI. But that project is still ongoing, so I think it's going to serve us better to talk and discuss the first two a little bit more. So to start, on this developmental changes in cellular microenvironment project, as I mentioned, this was evaluated using diffusion-weighted imaging. And specifically, there has been a series of advances in diffusion-weighted imaging over the past 10 years or so that have involved advances on the scanner acquisition side and on the post-processing modeling side. And what we really centered this project on was on advances in multi-shell diffusion imaging in particular. So classically, diffusion imaging has been done since the 90s. It's done on what's called a single shell. And the only difference between multi-shell and single shell diffusion imaging is instead of acquiring all of our images at one diffusion weighting or one radio frequency pulse strength, instead, we vary the electromagnetic strength throughout the course of the scan. And by having variable radio frequency pulses, by having a varying degree of strength by which we're eliciting signal from the tissue, we actually gauge different responses in the tissue. So one piece of tissue might look like something at one strength of the magnet, and then when we apply a different strength, we're able to glean additional information about that tissue and therefore the cellular microenvironment. So that's the advance on the scanner side, and then the advances on the modeling side really just incorporate the additional information that we're gleaning about brain tissue by administering these multiple shells or multiple diffusion weightings throughout the course of the scan. And we wanted to ask, given that diffusion imaging, particularly diffusion tensor imaging, has been robustly shown to relate to age, usually in the direction of individuals having more restricted microstructure corresponding to more restriction in water diffusion as they get older, we wanted to ask whether or not these new sequences and these new modeling techniques could be leveraged to better characterize neurodevelopment. So this really became the central question of this study. I'm not going to go through every brain metric and every modeling technique. It's just, I think, too many acronyms for a presentation where we're trying to do a broad overview. But color coding purposes, these diffusion tensor imaging techniques, which represent the most popular camp, the most popular way to evaluate cellular microstructure in vivo, are color coded in blue. And these newer modeling techniques that correspond to multi-shell diffusion specific techniques are going to be color coded in green throughout. As I said, I'm not going to go through each individual brain map, but just for reference, NODI is probably the most popular multi-shell method now, which stands for neurite orientation, dispersion, and density imaging. And MAPL, which is one that I really like, stands for Laplacian regularized mean apparent propagator MRI. So there's a few acronyms embedded in that one, actually. And for this study, we looked at all these different metrics across white matter networks, structural connectomes, as well as at each individual voxel in a white matter mask. But really the main purpose of this study is visible just when you're looking at the mean value of these maps within a global white matter mask. So really just for these next few slides, we're just going to be talking about the mean value of these white matter metrics across white matter. And then we track how that changes with age. And when we track how things change with age, we have to account for the nonlinearity, or often have to account for the nonlinearity of developmental effects, which can look something like this, where we have our measure of diffusion restriction on the y-axis and age on the x-axis. And the type of prototypical canonical developmental curve that we recover, which I think is reflected here, corresponds something to something akin to a rapid increase followed by a tapering off of that increase followed by a plateau, which is really why we bother with doing these nonlinear models in the first place. The thing that we can do with them, though, one of the cool properties that arises when you have these nonlinear models is you can look specifically where change is happening across the age range. So by quantifying the derivative or the slope or the change per year of this model fit at each point, we can build a confidence interval around that slope and evaluate when 0 net change per year enters our 95% confidence interval, which corresponds to where this horizontal bar becomes white. So we can see here across these two different multi-shell methods, we have our developmental curves, which show an increase, but a nonlinear increase in diffusion restriction over age. And the last thing that we can do with these nonlinear developmental terms is ascribe an effect size to them, which often at the end of the day is what we're interested in. And that effect size for these two metrics and all the other metrics evaluated is going to be on the y-axis in this bar plot, which shows the strength of the age effect associated with each diffusion metric. So what pops out here is that these newer multi-shell diffusion metrics are more sensitive to age effects, so they're picking up on stronger age effects than the most popular methodology, which is diffusion tensor imaging. So in this sense, the multi-shell diffusion methods do appear to be more sensitive to age effects. But this really became a dual-pronged argument with this next set of analyses. I know everyone's not terribly interested in head motion, but it's obviously very important for studying MRI and really important for studying developmental MRI in particular, because head motion tends to induce bigger effects on our brain metrics of interest than development itself does. And in this example, which is a known finding already, that fractional anisopatry, kind of the popular method of quantifying diffusion restriction, decreases as you move your head more, and head motion being on the x-axis here. This might not be terribly surprising since we're looking for organized patterns of water diffusion. So if you're moving your head around in the scanner, it's going to look like less restricted of a diffusion environment. The problem arises in that this is the same effect that we see with age. As you age, your diffusion becomes more restricted, and head motion is associated with less restriction on that diffusion. And finally, children move their heads more in the scanner. So we have the systematic confounding between head motion and the true developmental effect, with both of them having the same type of relationship. And you can do things like try and control for head motion in a linear model. You have a head motion term and then your age term separately. But ultimately, we'd really prefer that our brain metrics aren't systematically confounded by data quality in the first place. And that's exactly what we see with some of these newer diffusion metrics from the multi-shell models, that they don't have such a relationship to head motion, conferring them as kind of having a dual benefit of being more sensitive to age effects and less sensitive to the confounding influence of head motion. So that's the main takeaway from this first study. Can multi-shell diffusion be leveraged to characterize neurodevelopment any better? We say yes, both because it's more sensitive to age effects and less sensitive to the confounding influence of head motion, which usually is going to be the strongest inducer of artifact in our data. So I'm going to move on to the next study. If anyone has a question on that one, feel free to interrupt. But this was a nice way for me to get my feet wet and do some developmental modeling in grad school and kind of start to tinker with this idea of lifespan development. But it's ultimately quite reductionistic. Here we have one individual at one point on the x-axis corresponding to one point on the y-axis. Or another way of saying that is one individual is at one point in development at one point in time. In reality, increasingly, evidence is emerging that we're at multiple points of lifespan maturation concurrently. And I'm going to pull up another schematic here so we don't have to rely on my articulation for making that idea clear. This is a really nice review from Francis Lee from Science in 2014, just kind of showing this idea and the plausibility of this idea. So if we're looking at change in development, what people have noticed is that lower order areas, be it sensory motor cortex, or any other lower order brain area, tends to develop more rapidly and reach peak maturation prior to higher order areas like prefrontal cortex, which undergo a more protracted developmental time course. So all they're making the argument for here is that these lower order areas are more advanced in their maturational trajectories than higher order areas. So in this sense, let's say you're a 7-year-old on this schematic, you can see how different parts of your brain are in different phases of lifespan maturation at the same time. And this is particularly relevant for functional networks, or at least that's what we thought looking at the aging literature before starting this product, because we've seen some of these arcs in lifespan functional network segregation. And we've seen that they appear to be staggered as the schematic posits. Here's an example showing sensory motor systems, again, one of these lower order hierarchical systems relative to association system segregation, which is higher order networks like the default mode or frontoparietal networks. And what they're showing here is that after reaching their peak earlier in development, their peak functional segregation, these networks decline in aging, but that decline happens first in these lower order areas, which are again more advanced in their maturational trajectories. And although this is part of normative aging, it's critical because it does appear to mediate cognitive decline. This is just a nice review that ties together some of this functional dedifferentiation, that's a loss of segregation in this instance, and how that's tied into structural changes, as well as cognitive decline in old age. And actually it mediates cognitive decline from the studies we've seen so far in both healthy aging and in neurodegenerative conditions, more dramatically in the latter. So all that being said, we wanted to ask the question of whether or not on the developmental side, this type of functional network segregation or reaching its peak functional segregation would be staggered across a normative cortical hierarchy. But you can imagine slicing the brain up into sensory motor cortex, parietal and temporal association cortex, and prefrontal cortex is probably a little less nuanced than what's actually going on. So we wanted to try and pull this theoretical cortical hierarchy from existing data and see how it aligns. Specifically, I pulled in this principal gradient. Many of you are probably familiar, but just to recapitulate the main point of this paper here, what they did is pulled out a latent component that explains variance in bold signal covariance. So really just starting with a between vertex connectivity matrix, they pulled out a latent component using a fancy method that explains variance in bold signal covariance. And after doing so, they noticed that the component that they pulled out, pictured here, systematically lines up with a continuum of lower order to higher order psychological functions. As assessed by neurosynth meta-analyses, they found that areas that were low on this percentile binning or low on this gradient were systematically related to motor, eye movement, visual perception, and pain types of studies, whereas areas that are high on this principal gradient were systematically related to things like social cognition, emotion, verbal semantics, and autobiographical memory. Another critical component that they discovered of this principal gradient is that functional networks themselves appear to be organized to some extent across this principal gradient, with default mode networks tending to lie high on this gradient, and motor and visual networks tending to lie low on this gradient. And there's a few more interesting bits here. They found a repeated motif of a transition from a primary sensation network to an attention network to a frontoparietal network to the default mode network at several points across the cortex. And they offer kind of a broader organizational scheme for networks within this framework. But the main reasons that we wanted to adopt it here was A, it's obviously very highly related to bold signal organization or functional organization of the brain more broadly. That's where the component comes from. B, it lines up well with this theoretical hierarchy of lower order to higher order brain networks, as they showed in the neurosynth meta-analyses. And it also seems to be incredibly relevant for functional networks, or at least differentiating functional networks along this axis. So the central question here was, does developmental functional segregation adhere to this normative cortical hierarchy? And because we're interested in outcomes that are relevant to the mental well-being of the participants, we also wanted to know how this type of normative process could be supporting the development of executive function, which is often dramatic over the age range we studied, 8 to 23 years old. So there's a heavy focus on methodological rigor in this lab. So we wanted to take 2 steps before we proceeded with asking the developmental questions. The first was assessing and ultimately addressing the multi-scale organization of the cortex and accounting for that in our analyses. And what I mean by multi-scale in this context is when you come across different studies of functional networks, sometimes you'll find that they started with a 6-network solution to the brain, sometimes they start with a 7-network solution to the brain, 13, 17, 20, so on and so forth. And with all the reproducibility problems that we've seen in fMRI, we wanted to ensure that our somewhat arbitrary choice of scale, not to say that some scales might not be better than others, but we wanted to ensure that our choice of scale would not limit the generalizability of our results, so that we'd be able to better extrapolate our findings across studies and they wouldn't be necessarily scale dependent, but also just to deal with the true multi-scale organizational nature of the cortex. So to do that, I delineated these group consensus functional networks across a multitude of scales, again, which means number of networks in this context, starting with a very coarse delineation of the brain into essentially two different networks, which looks something like an association versus lower order parcellation of the brain, all the way to a very granular 30 network solution to the brain, where we're really getting into things that almost start to look more like parcels than functional networks. And I have a few example scales pulled out here so you can see them. But for the main analyses of this study, we analyzed across all scales, not just the ones that are pulled out. So that's one thing that we considered somewhat of a limitation of previous attempts at answering some of these questions. Another arises around this idea of personalized functional neuroanatomy. And this really started at Stanford, so I'd be interested to hear what all of you have to say about it as well. But the idea starts with that even after you account for the anatomical variability between individuals, even if you have great co-registrations, which I think we do now, I think the software is there for great structural co-registrations, but even after accounting for that, individuals still exhibit differences in where their functional territories are. And you can see this in Russ Poldrak's brain or in the Midnight Scan Club, but ultimately we've seen this phenomenon across studies, but it hasn't fully been accounted for yet, particularly in a multi-scale context. This is particularly important for studies of development. We have just shown that older individuals tend to have a different spatial layout of their functional networks than younger individuals, which tend to manifest as slight differences near the boundaries of the networks rather than core shifts in functional organization. But nevertheless, we wanted to ensure that any differences we observed in segregation or integration were truly due to differences in the coupling between networks, rather than just aliasing in differences due to the changes in these spatial boundaries over development. So to do that, I delineated these individualized functional networks for each subject over each scale. Here are 3 example subjects across 4 example scales. And then the bottom row is a map of individual variability in the spatial layout of those functional networks. So before we're talking about connectivity differences, we can see that individual variability has somewhat of a similar pattern over scales. And this has been found before, that individual variability tends to localize to higher order cortices when you're talking about the spatial layout of functional networks. To quantify that here, I use this principal gradient that I mentioned, with higher, more yellow areas being higher order, lower order areas being darker. And specifically just took the spatial correlation between this map of individual variability and this map of lower order to higher order function across scales. And after doing our null permutations and correcting for multiple comparisons, you can see the results of those spatial correlations as these colored points here. So after correction for multiple comparisons, most scales do exhibit this phenomenon where individual variability in the spatial layout of functional networks tends to be higher in higher order areas. But like I said, this had somewhat been shown before, although at single scales. I think the interesting bit here comes when you look at the second order relationship between these colored points. So taking those same points and just plotting them on a smaller scatter plot here, you can see that second order relationship where the spatial correlation between individual variability and a lower order to higher order continuum actually becomes higher over scales. So individual variability increasingly localizes to higher order cortices at finer scales. We think this one is important because it represents 2 factors that are predominantly unaccounted for in the literature: the multi-scale organization of the functional connectome and individual variability in the spatial layout of functional networks. We're showing that they systematically interact in the background. So what we might be missing by excluding one of those considerations independently might not be as great as the sum of their parts. But as I mentioned, this was all really to make sure that we were accurately characterizing neurodevelopment, because we're really interested in this idea of segregation versus integration over the lifespan. So that's what we did next, was applying this principal gradient again, this time to evaluate each network across scales, or how higher order or lower order it was on a continuum. So 464 networks was the total number that we derived across all scales 2 to 30. And each network was evaluated just by taking the average value of this map within the boundaries of each functional network. And when you lay out those networks, which I'm going to do on this plot below, you can see systematic patterns kind of arise over age. So each line here is a network. This is not subject level data plotted. This is all 464 networks, kind of colored by where they lie on this functional hierarchy. And I'm going to project the data, or the model fits from our data, I should say more specifically, back onto the brain just to show you what between network coupling is fit as in our models at 10 years old versus 21 years old. So if we take this between network coupling metric, which is the same thing as between network connectivity, it's just a linguistic difference, we can see a few things start to emerge early on here. The first is that before we even consider developmental effects, just by averaging between network connectivity over scales, we recover something that looks very similar to this unimodal to transmodal gradient. And that's even though this was, after we co-registered it to FS average 5 space, it's from an entirely different study of entirely different subjects. And they employed a pretty fancy methodological pipeline to derive these in the first place. But the fact that we were able to recover essentially the same pattern just by averaging between network connectivity over scales suggests to me at least that this is somewhat canonical of a feature of functional organization. The second thing that you might notice is the age effect itself, that this unimodal to transmodal gradient becomes increasingly embedded in the functional connectivity of our networks as one ages from 10 to 21 years old. More specifically, what I mean by that is that between network connectivity becomes systematically more aligned with this unimodal to transmodal gradient. These lower order areas continue to increase in their between network connectivity or integrating with the rest of the cortex. And these transmodal areas tend to decrease in their between network connectivity from the rest of the cortex, becoming more segregated. So in this sense, the functional connectome is increasingly differentiating across this lower order to higher order hierarchy over the age range that we sampled. And probably the best way to look at this effect is to take functional hierarchy and put that on the x-axis rather than using it as color coding. And then I'm going to put the age effect associated with between network connectivity on the y-axis. Just done here. So networks that are above 0 are integrating with age, networks that are below 0 are segregating with age. And this band of gray points here are those that are not significantly changing with age after correction for multiple comparisons. And we were happy with how this came out because it suggests that most variability in the developmental effects we were observing was explained by where each network was positioned on this unimodal to transmodal gradient. And just to tie it back to the literature I invoked earlier, the aging literature, I've inverted this plot. It's the same exact data, but now instead of a measure of functional integration, as in the case for between network coupling or connectivity, it's a measure of functional segregation. And maybe you can start to see the lifespan arcs that I think we're seeing and that we connect to the aging literature and the discussion and all of that. And that is knowing that these functional networks reach their peak segregation at some point in development and then descend for the rest of the lifespan, and that we're seeing this type of staggering of these lower order networks apparently being more advanced in their maturational trajectories. We thought we were really picking up on a lifespan phenomenon here rather than something specific to the age range that we were looking at, although the timing that different networks are in is specific to the age range we're looking at. If you're like me, you might be initially skeptical that these lower order networks are past their peak development for the rest of the life from the young age of 8 onwards. But there's really 3 things that give me more confidence in making that conclusion. The first is that it's only the lowest order networks that exhibit this type of past their peak at a young age property. So it's only the networks that we would expect to be the most advanced in their maturational trajectories that are showing this early descent. The second comes from the cortical thickness literature, which I think people were probably very surprised to see how quickly that descends from a very early age, indicating that a peak in development of one brain metric might not correspond to a psychological peak or a maturational peak as we're used to thinking of in terms of looking at the function of individuals. And the third piece of evidence really comes from the cognitive analyses. So let me wrap this up and then I will dive into those. But just on this first section, does developmental functional segregation adhere to normative cortical hierarchy? We said yes, to the extent where we can actually explain most variability in developmental functional segregation versus integration based on where that network is in a normative functional hierarchy. But onto the cognitive analyses, I think the easiest place to start from is to take this same plot and then put the executive function effect on the y-axis. So after controlling for age, what does the segregation versus integration of these networks, how does that associate with executive function scores, which again are derived from this cognitive battery, so kind of across a host of a dozen or so tasks. And we can see some similarities and some differences in the executive function effect derived after controlling for age. The similarities are maximal at the far right end of this plot. If we're looking at the most transmodal or the highest order functional networks, default mode networks, we see common ground. Default mode networks segregate with age, and segregation of default mode networks is associated with enhanced executive function even after controlling for age. So that part lines up. The far other end of the hierarchy, for the lowest order networks, we see dissociability, however. So these lower order networks, predominantly motor networks, dorsal attention networks, are becoming more integrated with age, but that integration is actually negatively associated with executive function after controlling for age. So no matter what age you are, after you account for how far along in the maturational sequence your brain network should be, you're better off having further segregated or further differentiated lower order networks here. That's what our analysis suggests. But this got somewhat confusing because we have a mixed bag of some networks apparently supporting neurocognitive development, some networks potentially suppressing neurocognitive development. So it kind of lent itself to a mediation framework where I could piece apart the contribution of each one of these networks separately and look for the roles that they might be playing. So by using this somewhat straightforward mediation triangle and just a straightforward product of paths approach to calculating mediation weights with neurodevelopment leading to increases in executive function, this is just the 23-year-olds do better than 8-year-olds on cognitive tasks phenomenon. But we're positing that a part of that cognitive development might be mediated by the refinement of functional networks that we see during the same age range. And when we do that and recover the AB path coefficient for each one of these networks, we see an alignment with the functional hierarchy as well. These points here representing what I was referencing with default mode segregation being associated with age and associated with executive function, so being one potential way by which normative neurodevelopment might mediate normative cognitive development. But at the far left end, we see fairly good representation of these unimodal networks, which our mediation analysis suggests are suppressing normative cognitive gains that are increasing during this time period more broadly. And there's kind of some heterogeneity between plots here, and there's a lot going on. And I'm just going to pull in one more figure, and then I think there's actually a pretty parsimonious solution to all of this that holds across the aging literature as well. But just for this last plot, which is just the change per year plotted onto the brain at the different ages that are kind of tertiles, I guess, of the age range that we sampled, you can see the segregation in blue. So these networks are segregating at these ages, it tapers off. These networks are integrating across the lifespan that we sampled. It didn't really taper off by 23 years old. And there's one common property between these relationships and the relationships to executive function. And that is that functional network differentiation, or the segregation of functional networks across the board, is supporting increases in cognitive function. And that's exactly what the aging literature found as well. If you remember me talking about loss of segregation mediating cognitive decline, we see the opposite here in that gain of that segregation is mediating cognitive ascent. So though it's a mixed bag, your brain's at multiple points in development at the same point in time, across the board, we're seeing that. So that gives us confidence that we can connect this to the aging literature and more broadly to lifespan maturation. So just to wrap up this study real quick, the first question was about whether or not developmental functional segregation adheres to this normative cortical hierarchy. And the second bit was on whether or not this supports the development of executive function. To the first, we found yes, and to the second, yes, but it's specifically that functional segregation that is supporting the development of cognition rather than the de-differentiation that we're observing in the lowest order networks. I'm just going to check how I'm doing for time really quick. Looks like it has been about 35 minutes. So
yeah, you're good on time.
Excellent. Any questions so far?
I do have a question. It might be a silly question, Adam, but when the plot on the right, when you see, it looks like the default mode network, why do we see it around 0 and around around 6? Does that lend you to question the default mode network? Or does it give you confidence in it? What do you think about that part?
Definitely, yeah, and that's absolutely not a silly question. All right, I hope not, because that was one of my first when it came up. So this is actually answerable if you go to a finer granularity of parcellations. There's Yo7 and Yo17. If you look at it consistently, these are medial temporal networks, which there's some argument as to whether or not those are truly default mode networks. They're not in the Yo17 parcellation, but they are in Yo7. So pretty consistently, these mid-range default mode networks are those that are occupying the most lateral aspects of the temporal lobe, rather than like the precuneus, posterior cingulate, angular gyrus kind of default mode networks. So there definitely is a dissociation there, but fortunately it lines up with those being noted as dissociable by other people as well.
Great, thanks. Okay.
And Leonardo, you have a question as well?
Yes, thank you. These are really wonderful data, and I really look forward to seeing this in print. It's super exciting. I had a question on slide 21. You show the network coupling and its relationship with age. Yes. So I wonder, what is your y-axis there? Like, what's that quantity?
Absolutely, yeah. That's a good question as well. This was also something we had to deal with a little bit. But it's really just a product of averages. So we take our between network coupling, let's say we have a 7 network solution to the brain as a correlation matrix between those 7 networks, right? So our diagonal is 1, and then we have 7 networks and they're like average connectivity to each other. So this is really just the average external connectivity.
Right.
So we have to average over that again.
Right. And when you say connectivity, you mean a correlation coefficient?
Yeah. Exactly.
And so then my question becomes, with a correlation coefficient of maximum 0.05, can we truly speak of coupling?
Yeah, absolutely. I will say that if we started in some instances where we did start with the average time series for a territory rather than just averaging the, right, let me try and rephrase that. So there are 2 ways to approach this. The first would be to generate the time series for each network and then correlate the time series from each network. And when you do that, you do get higher correlations than what we're displaying here. We found this across scales. But here we're starting with the kind of 10K, 10,000 vertices on the FS average 5 surface. So we're getting slightly lower values because we're looking at the average correlation across vertices rather than collapsing them into a time series and correlating it, I think. I don't know if that partially answers your question, but that is one thing.
Yeah, I would almost think that it might depend on your parcellation, right? Because I mean, depending on the method you use there, it might be that the parcellation is somehow enforcing the network time series to not be correlated. And so I am not that surprised, depending on the parcellation method you're using here, the clustering algorithm or whatever, that these correlations might drop significantly if you're enforcing that type of constraint. I was just surprised to see such small numbers because, on the whole brain level, I would expect to see something like 0.2, 0.3, but these seem pretty low. So that might be a thought, but I don't know. But thank you. That's a great point to make. Thank you.
Yeah, I hope that was helpful. Obviously, I haven't completely figured out functional time series and covariance in the brain, but I think you're right that the method could be contributing, although it's slightly less enforced orthogonality than ICA or something like that. But yeah, that's just the only note that I have that might be helpful, is that when we started with averaged time series, we did see stronger correlations rather than when we were taking the average values of each vertex in network A's correlation to each vertex in network B's. That is a good consideration moving forward, though, to think more critically about those numbers. Cool, so that takes me to the end of this study. As I said, I'm not going to dive a ton into this last study, but I want to talk about it briefly because it really is a direct spin-off from this previous study that I've done here. So we're here in the lifespan maturation arc, and now we know that each individual is actually at multiple points in development concurrently rather than just at one point along the x-axis. And this has really well captured this type of what brain area is ahead of others in the maturational trajectory by this principal gradient. So these higher order areas are more delayed in their phase, and these lower order areas are more advanced in their phase. And there's been a few papers, particularly in the past year, that have offered a hint to where this functional organization might be in part emanating from in the cortex. And it suggests something similar, that it might be that these lower order areas are systematically more advanced in their phase than these higher order areas, but at a much shorter time scale over the time course of single scans. And let me again show you what I mean here rather than rely on my articulation only. This is what's called a quasi-periodic pattern, where they just take the entirety of a time series, try and find the most recurrent pattern, and then look across sessions for a subject, try and find the most recurrent pattern in the bold signal for a subject. And then they look across subjects and try and find across the entire study, in this case, HCP, what is the most recurrent pattern in the time series. And what they found here over the time course of about 25 to 30 seconds, with warm colors representing more bold signal, cool colors representing less, was that the most prominent pattern in the data was a procession of bold signal along this cortical hierarchy. I'll play it one more time. You can see it starts in these lower order areas, and these higher order areas are hit systematically towards the end. And they quantify this by taking the time it takes for each vertex to peak, so how long it takes for each vertex to reach that regional peak. And then they correlated that with the principal gradient, just to show that they're very overlapping. The spatial correlation is 0.91, so strikingly high. Similar study, also 2021, found this principal delay profile where they're looking at the time it takes a region to peak relative to the global signal peak. So for each global signal peak, is this area systematically peaking ahead of the global signal, systematically peaking before the global signal, or neither? And what they found was this principal delay profile with, again, these lower order areas being more advanced and when they were peaking relative to these higher order areas. And here they found an even stronger correlation between this and the principal gradient, 0.93, suggesting that this really might be a fundamental property underlying organization along this axis. And this is probably best depicted in this graphical abstract from Ryan Rout out of Marcus Raichel's lab, where they're showing the procession of this normative waveform across the cortical hierarchy in line with functional networks, where we can see that covariance in functional networks might also be augmented by covariance in bold signal that comes from these functional networks being hit at the same time by a wave propagating across the cortex. This is the infraslow cortical oscillations piece. There's a lot going on here, but in general, the idea is that infraslow oscillations taking place at the time scale of 20 to 40 seconds could be inducing some of the covariance that we're observing in functional territories across the brain. And the really cool bit, I think that really helps tie this in to neurophysiology more broadly, is that these bottom two studies from Ryan Rout and Yameng Gu use monkey ECOG data to kind of establish what type of impact these slow oscillations might be having on faster waveforms that we're more used to dealing with in neuroscience. What they found is that it was systematically associated with gamma oscillations, where these slow waves were peaking, it was facilitating gamma oscillations, and when these slow waves were reaching troughs, that was suppressing gamma oscillations. So it was entraining these higher frequency oscillations, providing kind of a parsimonious way in which we might expect faster brain oscillations to be linked to what we're observing on fMRI timescales. So I've started to replicate this in ABCD. This is the main finding from Yameng Gu's paper, this correlation distribution here. And what this is showing is that a series of correlations associated with those global signal peaks, and you would imagine a positive correlation if areas that are high in the cortical hierarchy are highly delayed from the global signal peak. And you would expect a negative correlation if areas that are low in the hierarchy, like your motor strip or V1, are those that are delayed from the global signal peak. So a positive correlation is indicative of a type of bottom-up propagation, where the higher order areas are the most delayed and when they're peaking. And a negative correlation is indicative of a top-down propagation, where the lower order areas are the ones that are hit last in these cortical propagations. So I was able to recover this same distribution for ABCD, or a similar distribution for ABCD, just looking across resting state in these instances. And we see both modes present here, where bottom-up propagations, positive correlations appear to be more prominent, but these top-down propagations are also present in the data. So the interesting bit here, I think, is that this relationship seems to reverse in task data, and this hasn't been shown yet. This is for monetary incentive delay, but it's also true for the other tasks, where actually top-down propagations become more prominent than the bottom-up propagations do. And anytime you encounter something that might dovetail nicely with our psychological understanding of top-down and bottom-up processing, and you see that actually reflected in the brain, it's very exciting to me, at least. So that's what I'm hoping we're onto here, but we have more detail to do, And actually, this project is in HCPD now, so there's still a lot to do to wrap it up, but I think we've made some good progress. I'm actually going to skip over this next slide for time's sake, because I'd like to
We have
talk
about 5 minutes, Adam, but I'm sure we've already had some discussion, so feel free to just take a couple more minutes.
Okay, great. Yeah, I will just briefly detail this. This is kind of where the project is at now then. I'm using this principal gradient to derive a map of directionality using a calculus gradient, which is just a way where you can take any image and evaluate what the path to the most direct path to ascent in image intensity is. So essentially I can get a measure of which way points up in the cortical hierarchy from each spot in the cortex, and a measure of which way points down. Then I'm using this computer vision technique called optical flow to delineate the directionality of bolt signal, just how that travels across the cortex, and looking for systematic alignment for the direction that bolt signal is traveling, and hierarchical ascent, so traveling up in this type of bottom-up processing, or down in this type of top-down processing. And pretty consistently across subjects, we're seeing this bimodality with bottom-up represented by this 0 mark, where there's no distance between the direction bolt signal is traveling and the direction of going up in the principal gradient. And we're seeing a smaller, but also a peak around anti-parallel, indicating the top-down processing. And just within the past week, we found our age effect, that this might be explaining some of the age effects noted in the previous paper, because these waves become more prominent with age, or they seem to. And just today, actually, we got some face level or vertex level results in, suggesting that there's different parts of the cortex that are becoming more prone to these hierarchical waves over development. So still very much in development, but this is what I'm excited about and going to be doing for the rest of grad school, besides paper revisions and stuff like that. More broadly, I wanted to talk about what I'm hoping to do moving forward. And this really starts with the popular, like, kind of NIMH encouraged format of a study, I think, where we look at a symptom that we're interested in and how that scales with the brain, right? So we're fundamentally asking the question, how do individuals with psychopathology look different than healthy individuals, whatever that might be, right? So by taking this type of matching a cross-sectional profile of symptoms to a cross-sectional profile of how the brain looks for different people, we are picking up on these meaningful and kind of like great windows into how psychopathology scales across individuals. But fundamentally, the contrast that we're drawing is, how are individuals with psychopathology different than individuals without psychopathology? And I think with the place we're at with data accessibility, with things like ABCD, but also with PIs aggregating massive amounts of data and massive curation efforts like those from Dr. Tosi, we can start to ask a new set of questions. So instead of asking how individuals with psychopathology are different, we can start to ask how they get better specifically, or on the preventative medicine side, how psychopathology emerges in the first place. And I think the way we can do that is by looking at how changes in the brain are coupled to changes in behavior. So in something like ABCD, where we're following individuals from 9 to 10 years old, 10 years down the road, we can take these longitudinal time points and extract out symptoms or profiles of symptoms that are changing over development, which we would expect to be related to ADHD and conduct disorder and anxiety disorders in this age range. And I have seen that. That does seem to be what's going on between time point 1 and time point 2 in ABCD. And we can look at how their brains are changing in tandem with the emergence of psychopathology. So by drawing up our models like this, we can explicitly make contrast for how individuals with psychopathology have that psychopathology emerge. Or I think even more excitingly, in something like the data set that's been aggregated from Lee's work, we can start to ask how psychopathology remits. How do individuals get better, rather than just asking how individuals with psychopathology are different than individuals without it. So I'd like to move into that moving forward if opportunity allows. I still have a ton to learn about psychopathology in particular, so I'm not set in stone on any of this. But thanks to all of you for listening, and it's really been an all-star cast here. I've been incredibly lucky to work with who I have worked with since coming here. I'd recommend all of these people. And I'm really grateful for the opportunity I had here and before as a research coordinator, and moving forward as well. And thanks again to all of you for listening, and I'm happy to take any more questions.
Thank you, Adam. Fantastic presentation. and really exciting to be thinking about how to create the models for that relationship you're describing. Like, how do symptoms develop and how do those map onto the brain changes at a very individual level? So let's turn to questions. I think someone had their hand up. Jump in if not. If I can't see it, this floor is open to questions. Donna, go
I
ahead.
have a question. Back to the, you talked about the multi-shell diffusion versus the single shell. Not really familiar with it. I'm just wondering, besides decreasing the head motion, or you're getting a better signal from head motion, does it have anything to do with the ability to capture diffusion around the edges? I've heard a little bit about the corners sometimes are difficult to quantify.
It could. I mean, I didn't systematically look at how this varied by directionality of the diffusion or kind of the edge cases. It definitely could, though, especially that last method that I called Laplacian regularized mean apparent propagator MRI specifically has regularization built into it to deal with certain things like that. And I think it's able to perform to the extent that it does because it has more data points in space to be able to fit to, because you have these different tissue responses across different shells. So I think part of that probably could help smoothing over some of the edge cases you're talking about. I just didn't look at it explicitly.
Might be something interesting, yeah.
Thanks.
Have a few broader comments, Adam, and just something that potentially we can follow up on in more detailed discussions. One is at the kind of level of the field, what I think is really exciting with what you're doing and the opportunities for psychopathology is, how do we find metrics that we can use to quantify individuals that still have like meaning in terms of the functional neuroanatomy and the anatomy, and this connecting some bigger arcs. But one way I've thought about it is all of the ways that in neuropsychology there's been a kind of historical development around how do you get different hierarchical measures, in a sense, like some that are composites and large scale averages that would be like global sense of neurocognitive function, and then it can be broken down into domains like verbal, nonverbal, and those can be broken down into very specific measures. But a lot of thought has gone into how do you develop norms and standards so that you can generate interpretations of individual profiles. Do you see analogies in how you're thinking about it? Because also in neuropsychology, you think about development as well, like how things are changing over age, really important context.
Yeah, I obviously don't have a complete answer for any of that, but I appreciate the invitation for speculation. I've struggled with this a bit myself in dealing with some of the factor scores here. There was a period where I was looking at Tyler Moore's factor scores, which kind of has this nested G, like general factor versus more specific ones. And it got particularly tricky with the psychiatric factors, because we had essentially like a broad psychopathology factor nested within that with these other psychopathology factors. But being able to interpret what anxious misery means after you're controlling for overall psychopathology. And actually that was one area where we saw some of the strongest relationships, which was anxious misery after controlling for overall psychopathology. It definitely muddied the waters a little bit. So I guess this is one area where I'm more eager to learn from clinicians and people who have to implement these, because I think clarity in that situation is probably something we should be focusing on as something to drive it otherwise. So I don't know if like my point of reference is particularly, I don't know if I have a better answer for it at the moment.
I think that's great speculation, and there's not currently an answer. So I think it's a really rich area for discussion, including that you showed how you need to take account of interactions between networks, which is not typically thought of in other domains, that you, at least not that I'm aware of, you're not looking at interactions between neuropsych behavioral measures, you're looking at them within domain. So a lot of thoughts. One other comment, which is just something that you may already know about or may be relevant, is in those gradients you see with the change in the segregation and connection, it made me think of the findings from some EEG work, which you may be familiar with, where they look at what they call traveling waves that follow. Are you familiar with that work?
Not as much as I should be, but Ariel has actually pointed me towards some of that, and it's been very promising so far.
Great. Okay. So let me see if anyone else has got thoughts, comments.
I have a question, Adam. Very nice talk, and I look forward to working with you on the longitudinal studies. I have a question related to the slow propagation or wave you have described as the third project. Do you think that might be a source of dynamic functional connectivity people observed in recent years? Like, for example, people use sliding window of 1 minute to look at the dynamic functional connectivity, which somehow in the range of the frequency you have described. I also wonder about the origin of the slow propagation. Like, do you think it's related to the CSF washout, or like general, what do you think that might be the cause? Thank you.
Yeah, absolutely. There's a few interesting things to unpack there. First, on the dynamic thing, that's not my area of expertise, but I will note that there has been a few people who have stood out. Like if you look at Rick Betzel's Edge functional connectivity and how there are these giant spikes where they can reconstruct, 90% of the functional connectivity matrix by using these like tiny windows. That reminds me of this, because if you look at, either the Ryan Rout paper or Jonathan Power has something similar on this too, tying this to respiration. There are specific moments in the scanner where these big, like high Z-score, I guess, waves seem to propagate across the entire brain. And they might not be driving all the functional, they're definitely not driving all the functional covariance we see, but they seem to be recapitulating it more strongly, more rapidly in those short windows in association with breathing and attention throughout these papers. So I do think that when these waves happen, probably not as cleanly as shown in the group average templates, they are giving rise to the spikes in functional connectivity, or these short windows of functional connectivity where we can reconstruct a subject's entire FC matrix from a very short period of time. So I don't have a broader understanding of the dynamic FC world, but I have seen those types of like, this window right here recapitulates the entirety of this person's functional connectivity. And I've seen that tied with these waves through Jonathan Power and Rick Betzel's work a little bit, and the great work of the graduate students. The second question was on where in the brain specifically these are emanating from. I think Max Schein's work is probably my starting point for that. He's found some promising subcortical nuclei that seem to be associated with these global states of integration or segregation. And I think he has multiple papers out now, one of them coming out much more recently, showing the role of the reticular activation system in instigating some of these wave-like events. But it's tough because everyone calls them slightly different things, everyone's different scanner parameters, and everyone quantifies it a little bit differently. But those are some people's work that I look to for kind of A, tying it into dynamic FC, but B, tying it into more specific brain structures.
Thank you very much. And I'm happy to talk about the first question offline, because I've seen many differences in the different scales of dynamic functional connectivity. One is what you mentioned about the spikes, which is pretty fast. And the other one is like the sliding window dynamic functional connectivity. They show some very different aspects. And I wonder if like they actually originate from different sources. And I'm happy to chat more. Yeah,
looking forward to it. That'll be great. Thanks for your question.
Lots of food for thought offline. We have time for one final question, so please jump in if you haven't already and you have one. Sounds like not, and we're exactly on time, so perfect timing. Thank you again so much, Adam. It's really, really interesting data and beautifully presented. Lots of food for thought. So really appreciate your time, and thank you for joining us, and we'll definitely be following up.
Excellent. Thank you so much for listening, everyone. And thanks for the opportunity to come speak early. As I said, it means a lot. So looking forward to seeing more of you in a slightly more personal context or less virtual context soon too.
Wonderful. Okay. Have a good rest of your day, everyone.